Imagine standing in a vast library where you can only see the books within arm's reach, knowing that countless more volumes stretch infinitely beyond your vision. This is humanity's predicament when we gaze into the cosmos. We live within what astronomers call the observable universe, a sphere roughly 93 billion light-years across, containing everything we can possibly detect. But what lies beyond this cosmic horizon? The answer might be the most mind-bending revelation about reality itself. The story begins with a fundamental misunderstanding that persisted for millennia. Ancient civilizations looked up at the night sky and saw what appeared to be a celestial dome studded with points of light. They imagined the universe as a finite, enclosed space with Earth at its center. The Babylonians drew maps of their cosmos on clay tablets, depicting Earth as a flat disk surrounded by water and covered by a solid dome. The ancient Greeks developed more sophisticated models, with Aristotle proposing a series of crystalline spheres carrying the planets and stars around a central Earth. Even the great minds of antiquity struggled with the concept of infinite space. Aristotle argued against the possibility of an infinite universe, reasoning that it would make the concept of place meaningless. If space extended infinitely in all directions, how could you define up or down, here or there? The medieval Islamic astronomers and European scholars who followed continued to work within these finite, bounded models of the cosmos. The Renaissance brought new perspectives, but maintained the idea of cosmic boundaries. When Copernicus displaced Earth from the cosmic center, he still imagined the stars as fixed on a distant sphere. Galileo's telescope revealed mountains on the Moon and moons around Jupiter, expanding our sense of cosmic scale, but not eliminating the concept of cosmic boundaries. Even Johannes Kepler, who discovered the elliptical orbits of planets, speculated about whether the universe might be finite to explain why the night sky wasn't blazingly bright with starlight from infinitely many stars. As late as the early 20th century, most astronomers believed our Milky Way galaxy contained the entire universe. The great debate of 1920 between Harlow Shapley and Heber Curtis centered on whether the mysterious spiral nebulae scattered across the sky were part of our galaxy or separate island universes beyond it. Shapley argued for a large Milky Way containing all known celestial objects, while Curtis proposed that spiral nebulae were distant galaxies comparable to our own. This changed dramatically in 1925 when Edwin Hubble made a discovery that revolutionized our understanding of cosmic scale. Using the newly constructed 100-inch telescope at Mount Wilson Observatory, the largest in the world at the time, Hubble observed what astronomers called spiral nebulae. These mysterious cloudy objects had puzzled astronomers for decades. Some appeared structured and organized with clear spiral patterns, while others seemed more elliptical or irregular. Hubble's breakthrough came from his study of Cepheid variable stars within these nebulae. These stars pulsate with regular periods directly related to their intrinsic brightness, making them perfect cosmic distance markers. By measuring how bright these Cepheids appeared compared to how bright they should be based on their pulsation periods, Hubble could calculate their distances using the inverse square law of light. The results were staggering. The Andromeda Nebula, as it was then known, lay over 2 million light-years away, far beyond the accepted boundaries of our galaxy. This single measurement expanded the known universe by a factor of hundreds. What astronomers had thought was a small nebula within our own galaxy turned out to be another galaxy entirely, containing hundreds of billions of stars and comparable in size to the Milky Way itself. But Hubble's revelations were just beginning. As he studied more distant galaxies using increasingly sophisticated techniques, he noticed something peculiar about their light. When astronomers split light into its component colors using spectrographs, they could identify the characteristic fingerprints of different chemical elements. Each element absorbs and emits light at specific wavelengths, creating unique patterns of bright and dark lines in the spectrum. In the spectra of distant galaxies, these familiar patterns were systematically shifted toward the red end of the spectrum. This redshift, as it became known, indicated that the galaxies were moving away from us. The explanation lay in the Doppler effect, the same phenomenon that makes an approaching ambulance siren sound higher in pitch and a receding one sound lower. Light from approaching objects is shifted toward the blue end of the spectrum, while light from receding objects is shifted toward the red. Even more remarkably, Hubble discovered a clear relationship between distance and redshift. The farther away a galaxy was, the faster it appeared to be receding. This relationship, now known as Hubble's law, revealed a pattern that extended throughout the observable universe. Galaxies weren't just moving away from us randomly, they were participating in a systematic expansion of space itself. This discovery led to one of the most profound insights in human history. The universe is expanding. Space itself is stretching, carrying galaxies apart like raisins in rising bread dough. This wasn't just movement through space, but an expansion of space itself, with new space being created between galaxies as time progressed. The implications were staggering and counterintuitive, challenging humanity's deepest assumptions about the nature of space and time. This expansion implies that if we could reverse time like running a movie backward, all matter and energy in the universe would converge toward a single point. This realization gave birth to the Big Bang theory, our current best explanation for the origin and evolution of the cosmos. Belgian physicist Georges Lemaitre first proposed what he called the primeval atom, a singular state from which the universe expanded. The term Big Bang was actually coined by astronomer Fred Hoyle, ironically as a dismissive description of a theory he opposed. The expanding universe model immediately raised a puzzling question about cosmic boundaries. If the universe is expanding, what is it expanding into? This question reveals the limitations of our everyday intuitions about space and boundaries. We're accustomed to objects expanding into pre-existing space, like a balloon inflating in air. But the universe isn't expanding into anything external. Rather, space itself is being created as the universe expands. There is no outside, no edge, no boundary in the conventional sense. To understand this concept, imagine the surface of an inflating balloon. As the balloon expands, the surface area increases, but there's no edge to the surface. A two-dimensional being living on the balloon's surface would observe distant objects moving away, with farther objects receding faster, exactly matching what we observe in our three-dimensional space. The two-dimensional being would find no boundary to their universe, no edge beyond which nothing exists. Our three-dimensional space might be analogous to this two-dimensional surface, curved in ways we cannot directly perceive through higher dimensions we cannot access. Just as the balloon's surface curves through three-dimensional space while remaining two-dimensional, our three-dimensional space might curve through higher dimensions while remaining fundamentally three-dimensional from our perspective. This expansion has a crucial consequence that creates the central mystery we're exploring. It limits what we can observe. Light travels at a finite speed, roughly 186,282 miles per second, and the universe has a finite age of approximately 13.8 billion years since the Big Bang. This means we can only see objects whose light has had time to reach us during the universe's entire history. This creates a spherical boundary around us called the cosmic light horizon, or the boundary of the observable universe. Light from objects beyond this boundary simply hasn't had time to reach us yet. Every day, as time progresses, this boundary expands slightly, revealing objects that were previously beyond our observational reach. But this also means that vast regions of the universe remain forever hidden from our current view. The observable universe contains everything we can possibly detect using any form of electromagnetic radiation, from radio waves to gamma rays. Within this cosmic sphere, we can count roughly 100 billion galaxies, each containing hundreds of billions of stars. The total number of stars in the observable universe exceeds the number of grains of sand on all the beaches on Earth by many orders of magnitude. But here's where things become truly mind-bending. The observable universe, vast as it is, might represent only an infinitesimally small fraction of reality. Recent measurements of the cosmic microwave background radiation, the afterglow of the Big Bang, suggest that space is remarkably flat. This flatness has been measured with extraordinary precision by satellite missions like the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft. In cosmology, flat doesn't mean two-dimensional, but rather refers to the geometry of space. In flat space, parallel lines remain parallel across cosmic distances. The angles of triangles add up to exactly 180 degrees, and the circumference of a circle equals exactly pi times its diameter. This contrasts with curved space, where these familiar geometric relationships would be violated. The precise flatness of space has profound implications for what lies beyond our observable boundary. In mathematical models of cosmology, a perfectly flat universe extends infinitely in all directions. If space is truly infinite, then the unobservable universe beyond our cosmic horizon contains an infinite amount of matter and energy arranged in an infinite number of galaxies, stars, and planets. This infinity isn't just large, it's qualitatively different from any finite number, no matter how big. An infinite universe would contain not just more of what we see in our observable region, but literally every possible arrangement of matter and energy consistent with the laws of physics. This includes arrangements identical to what we observe in our cosmic neighborhood, and arrangements that differ in every possible way. Consider the implications carefully. If space is infinite and matter is distributed relatively uniformly as observations suggest, then every possible arrangement of particles within any finite volume must be repeated infinitely many times across the cosmos. The volume of space containing all the matter that makes up you, everyone you know, your entire planet, solar system, and local galactic environment would be replicated endlessly throughout the infinite universe. This isn't science fiction, but a logical mathematical consequence of infinity combined with finite possibilities. Within any finite volume of space, there are only finitely many ways to arrange a finite amount of matter. Atoms can only be configured in so many ways. Molecules can only bond in specific patterns, and even complex structures like brains can only be wired in a finite, though vast number of arrangements. In an infinite universe with uniform matter distribution, every possible configuration must occur infinitely many times. This means there are infinite copies of you reading these exact words at this exact moment, scattered throughout the infinite cosmos. Some are identical down to the quantum level, while others differ by the position of a single atom or the state of a single neuron. But the implications go far beyond mere copies. In an infinite universe, there would be regions where history unfolded slightly differently. Versions of Earth where the asteroid that killed the dinosaurs missed by a few miles, allowing alternative evolutionary paths to unfold. Planets where dinosaurs continued to evolve and developed intelligence and technology. Worlds where different species became dominant, where evolution took radically different paths, where the very chemistry of life developed differently. There would be versions of human civilization that made different choices at crucial junctures in history. Societies that never discovered fire, others that developed space travel thousands of years earlier. Civilizations that avoided wars, others that never developed beyond hunter-gatherer lifestyles. Every possible variation in human development, every alternative historical timeline, every different choice that could have been made at any point in history would not only exist but exist infinitely many times. On a personal level, there would be infinite versions of you who made different choices at every decision point in your life. Versions who chose different careers, lived in different places, married different people, or remained single. Versions who made better choices and versions who made worse ones. Versions who lived longer lives and versions who lived shorter ones. Every possible path your life could have taken exists as a real physical reality somewhere in the infinite universe. This concept, known as the quantum multiverse, or level 1 multiverse in the classification system developed by physicist Max Tegmark, emerges naturally from our best current understanding of cosmology, combined with the mathematics of infinity. It suggests that reality is far stranger and more expansive than we ever imagined, with our observable universe representing just one tiny region in an infinite cosmic ocean of possibilities. The mathematics of infinity allows for structures and possibilities that seem impossible in our finite experience. In an infinite universe, there could be regions larger than our observable universe that are completely empty, devoid of any matter or energy whatsoever. These cosmic voids would dwarf anything we observe in our local region, stretching for distances that make intergalactic space seem crowded by comparison. There could be regions where the initial conditions following the Big Bang were different, leading to the formation of structures unlike anything in our cosmic neighborhood. Areas where matter clumped together differently, where the first stars formed at different times and with different properties, where entire galaxy clusters evolved along alternative pathways. There could be regions where quantum fluctuations during the early universe's inflation created conditions that led to fundamentally different large-scale structures. While the laws of physics would remain the same, the particular solutions to those laws, the specific ways matter and energy organize themselves, could vary dramatically across infinite space. Consider the possibility of regions where dark matter, the mysterious invisible substance that makes up roughly 27% of the universe's energy density, clustered differently. In our cosmic neighborhood, dark matter forms a cosmic web of filaments and nodes that provides the scaffolding upon which galaxies and galaxy clusters form. But in other regions of infinite space, dark matter might have evolved into completely different configurations. There could be cosmic regions where dark matter formed vast, uniform sheets instead of web-like structures. Others where it concentrated into enormous spherical clouds, larger than galaxy clusters. Still others where dark matter interactions with ordinary matter proceeded differently, leading to hybrid structures unlike anything we observe locally. The nature of dark energy, the mysterious force driving the accelerated expansion of space, adds another layer of complexity. Dark energy comprises about 68% of the universe's energy density, yet its fundamental nature remains one of the greatest puzzles in modern physics. If dark energy properties vary across different regions of an infinite universe, the consequences would be profound. In regions where dark energy is stronger than in our cosmic neighborhood, space might expand so rapidly that it prevents the formation of any bound structures. Galaxies, solar systems, even atoms themselves might be torn apart by the relentless expansion. These regions would remain forever empty, devoid of the complex structures that make life and intelligence possible. Conversely, regions where dark energy is weaker or absent might experience fundamentally different cosmic evolution. The expansion might slow dramatically or even reverse, leading to eventual contraction and collapse. These regions might cycle through repeated expansions and contractions, creating oscillating universes with radically different histories and futures. The concept of infinity also allows for structures that challenge our understanding of complexity and organization. In an infinite universe, there would inevitably be regions where matter and energy organize themselves into patterns of staggering complexity and beauty. Structures that dwarf galaxies in scale, yet display intricate organization reminiscent of living systems. Imagine cosmic-scale organisms, patterns of matter and energy that extend across millions of light-years, yet display metabolism, reproduction, and evolution. These structures might be so large and slow-moving that entire civilizations could rise and fall during what corresponds to a single heartbeat of such cosmic entities. There might be natural quantum computers spanning galactic distances, utilizing the quantum properties of matter and space to process information at scales we can barely comprehend. These cosmic information processors might solve mathematical problems that would take our best computers longer than the age of the universe, doing so as naturally as water flows downhill. The possibility of Boltzmann brains presents one of the most unsettling implications of infinity in cosmology. Ludwig Boltzmann, working in the late 19th century, considered the implications of the second law of thermodynamics applied to an infinite universe. If the universe tends toward maximum entropy, thermal equilibrium, how do we explain the existence of ordered structures like stars, galaxies, and living beings? Boltzmann proposed that random thermal fluctuations could occasionally create ordered structures by pure chance. In an infinite universe with infinite time, these fluctuations would eventually produce every possible configuration of matter, including conscious observers, complete with memories of a past that never actually occurred. In an infinite universe, such randomly assembled brains would vastly outnumber brains that evolved through natural processes like biological evolution. The probability that any given conscious observer arose through random fluctuation rather than evolution becomes overwhelming in the face of infinity. This leads to the disturbing possibility that you might be such a Boltzmann brain, with all your memories of life on Earth being nothing more than random quantum fluctuations. While most physicists consider Boltzmann brains a problem to be solved rather than a likely reality, they illustrate the strange consequences of taking infinity seriously in physics. They force us to confront the possibility that our intuitions about probability, causation, and even our own existence might be fundamentally flawed when applied to infinite systems. The concept of measure problem in cosmology deals with how to assign probabilities to different outcomes in an infinite universe. When everything possible happens infinitely many times, traditional concepts of probability break down. How do you calculate the likelihood of any particular event when both the event and its absence occur infinitely often? Cosmologists have proposed various solutions to this measure problem, including different ways of counting and comparing infinities. Some suggest focusing on the density of different types of observers or events rather than their absolute numbers. Others propose that the measure problem indicates fundamental limitations in our current understanding of infinity and probability. The concept of cosmic infinity also intersects with theories about the very beginning of the universe. Inflation theory, proposed by physicist Alan Guth in 1981, suggests that the universe underwent a period of exponential expansion in its first fraction of a second after the Big Bang. During this inflationary epoch, space expanded faster than the speed of light, stretching quantum fluctuations to cosmic scales and setting the stage for the large-scale structure we observe today. Inflation theory elegantly explains several puzzling features of our observable universe. It explains why space is so remarkably flat, why the cosmic microwave background radiation is so uniform across the sky, and why we don't observe certain exotic relics that other Big Bang models predict should exist. But inflation theory also leads to even more mind-bending implications. In most models of inflation, the inflationary expansion doesn't end everywhere simultaneously. While inflation ends in some regions, allowing normal expansion and the formation of matter and structures, it continues forever in other regions. This eternal inflation creates an infinite number of bubble universes, each with potentially different physical properties. Our observable universe would be just one such bubble in an infinite cosmic foam of universes. Each bubble universe undergoes its own Big Bang-like transition from inflation to normal expansion, but the conditions during this transition might differ from bubble to bubble. The scalar field that drives inflation, called the inflaton, might settle into different energy states in different bubbles. These different vacuum states could correspond to different fundamental constants, different particle physics, even different numbers of spatial dimensions. The electromagnetic force might be stronger or weaker, the strong nuclear force might have different properties, or there might be additional forces that don't exist in our bubble. Most of these bubble universes would likely be sterile, devoid of the complex structures necessary for life and intelligence. If the electromagnetic force were too strong, electrons wouldn't form stable orbits around nuclei and atoms couldn't exist. If the strong nuclear force were too weak, protons and neutrons couldn't bind together to form atomic nuclei. The fine-tuning problem in cosmology refers to the remarkable fact that our universe appears exquisitely calibrated for the existence of complex structures and life. The fundamental constants seem precisely adjusted to allow stars to form, heavy elements to be created through stellar nucleosynthesis, and chemistry to produce the complex molecules necessary for biological processes. In a single universe, this fine-tuning might seem to require explanation, perhaps pointing to design or purpose behind the cosmic order. But in an infinite multiverse containing every possible combination of physical laws and constants, it becomes inevitable that some universes would have the right conditions for complexity and life. We naturally find ourselves in such a universe because universes without these conditions wouldn't contain observers to wonder about fine-tuning. This anthropic reasoning suggests that apparent design might simply reflect observational selection bias in an infinite multiverse. We observe a universe compatible with our existence because incompatible universes don't contain beings capable of making observations. However, the multiverse concept raises its own philosophical challenges that cut to the heart of scientific methodology and the nature of knowledge itself. If every possible universe exists somewhere in the infinite multiverse, does our particular universe have any special significance? Are there objective facts about reality if every possible version of reality exists somewhere? Some philosophers and scientists argue that multiverse theories are inherently unscientific because they make predictions that can never be tested or falsified. If we can never observe other universes or travel between different bubbles in the cosmic foam, how can we ever confirm or refute the existence of a multiverse? Science has traditionally progressed through theories that make testable predictions about observable phenomena. Others contend that if our best scientific theories predict a multiverse, we should take that prediction seriously, even if it challenges our intuitions about testability and reality. They argue that many accepted scientific theories make predictions about unobservable entities, from quarks to black hole interiors, and that unobservability alone doesn't disqualify a theory from scientific consideration. The search for evidence of the multiverse has become an active area of research, despite these philosophical challenges. Cosmologists look for potential signatures in the cosmic microwave background radiation that might indicate collisions between bubble universes. If our bubble universe had collided with another bubble in the distant past, such a collision might have left detectable imprints in the pattern of temperature fluctuations across the sky. They study the statistical properties of galaxy distributions and the polarization of ancient light for clues about the larger structure of reality beyond our observable boundary. Subtle anomalies in the cosmic microwave background, unexpected correlations in galaxy positions, or unusual patterns in the distribution of matter might provide indirect evidence for influences from beyond our cosmic horizon. Advanced gravitational wave detectors like LIGO and Virgo open new windows into the universe's hidden depths. Primordial gravitational waves from the epoch of inflation could carry information about the structure of reality at the largest possible scales, potentially revealing whether our universe is finite or infinite, unique or one of many in a vast multiverse. The study of cosmic topology, the overall shape and connectivity of space, provides another approach to understanding what lies beyond observable boundaries. While space appears flat locally, it could still have a complex global structure. Space might be finite, but curved back on itself in ways that create unusual topological properties. Imagine space as the surface of a torus, like a donut. Locally, the surface appears flat, but globally it has a finite volume and wraps around on itself. Light traveling far enough in any direction would eventually return to its starting point, creating multiple images of the same galaxies scattered across the sky. Astronomers search for such repeated patterns that might reveal the hidden topology of space. Other possible topological structures include Klein bottles, where space twists back on itself in more complex ways, or hyperbolic geometries that create infinite space with curved local properties. Each possibility would leave different signatures in the distribution of matter and the patterns of light across the cosmic microwave background. Recent discoveries have added new dimensions to our understanding of what might lie beyond the observable universe. Dark matter, which makes up roughly 27% of the universe's energy density, interacts only gravitationally with ordinary matter. This invisible substance could form structures and patterns completely alien to our experience based on ordinary matter. In our observable universe, dark matter appears to form a cosmic web of filaments connecting galaxy clusters and defining the large-scale structure of space. But in the unobservable universe, dark matter might have evolved into configurations impossible in our local region. There could be vast dark matter galaxies with no ordinary matter, invisible cities of exotic particles following their own complex evolutionary pathways. If dark matter consists of particles that interact weakly with each other, these interactions might become important only at densities much higher than those typically found in our cosmic neighborhood. Regions of the unobservable universe with different initial conditions might contain dark matter structures, dense enough for these interactions to create entirely new phenomena. There might be dark matter stars, held together by dark matter interactions rather than gravity alone. Dark matter planets orbiting dark matter suns. In dark matter solar systems entirely invisible to our telescopes, but potentially supporting their own forms of complexity and organization. Some theoretical models suggest that dark matter might participate in its own electromagnetic-like interactions, invisible to ordinary matter, but allowing dark matter particles to form atoms, molecules, and complex structures. In regions where such dark matter chemistry dominated, there might be invisible ecosystems of staggering complexity, dark matter life forms that evolved along pathways completely independent of ordinary matter biology. The concept of dark energy adds yet another layer of mystery to what might exist beyond our observable boundary. Dark energy comprises about 68% of the universe's energy density and drives the accelerated expansion of space, yet its fundamental nature remains completely unknown. It could be a property of empty space itself, a dynamic field that changes over time, or something even more exotic. If dark energy properties vary across different regions of space, the consequences for cosmic evolution would be profound. Regions where dark energy is stronger than in our neighborhood might expand so rapidly that they remain forever empty of any complex structures. The acceleration would overcome gravity at every scale, preventing the formation of galaxies, stars, planets, or even atoms. Conversely, regions where dark energy is weaker or has different properties might experience fundamentally different cosmic evolution. Some areas might undergo periodic changes in expansion rate, creating oscillating universes that expand and contract in regular cycles. Others might reach maximum expansion and then begin contracting, leading to eventual Big Crunch scenarios where all matter and energy collapse back into a singular state. The possibility that dark energy might decay or transform into other forms of energy over cosmic timescales adds another dimension of complexity. Regions where dark energy has already decayed might have evolved into post-dark energy phases of cosmic history that we cannot observe or imagine from our current vantage point. String theory, one of the leading candidates for a unified theory of quantum gravity and all fundamental forces, suggests even more exotic possibilities for what might exist beyond our observable universe. In string theory, the fundamental objects aren't point-like particles, but tiny one-dimensional strings vibrating in a space with many more dimensions than the three we directly experience. These extra dimensions might be compactified, rolled up so tightly that we don't notice them in everyday experience, but their particular configuration determines the fundamental particles and forces we observe. Different regions of space might have extra dimensions compactified in different ways, leading to effectively different physics and different types of matter and energy. Some string theory models predict a vast landscape of possible vacuum states, each corresponding to different ways the extra dimensions can be curled up and different ways the fundamental forces can be unified or separated. This string landscape could contain 10 to the power of 500 or more distinct possibilities, each giving rise to different fundamental particles, different forces, and different physical laws. In an infinite universe undergoing eternal inflation, all of these possibilities might be realized somewhere. There could be regions where extra dimensions are partially uncompactified, allowing matter and energy to move through dimensions inaccessible to us. There might be areas where the fundamental forces unify at energy scales much lower than in our region, creating physics fundamentally different from anything we observe. Imagine regions where gravity works differently because extra dimensions are configured in exotic ways. Places where electromagnetic forces operate through additional spatial dimensions, where the strong nuclear force has different symmetries, or where entirely new forces emerge from the interaction of matter with extra-dimensional geometry. The concept of brane-world cosmology, emerging from string theory, suggests that our entire four-dimensional universe might exist on a higher dimensional surface called a brane. This brane floats in a higher dimensional bulk space that might contain other branes with their own universes and physical laws. If multiple branes exist in the bulk space, there might be ways for them to interact despite being separated in higher dimensions. Gravitons, the hypothetical particles that carry gravitational force, might be able to travel through the bulk between branes, creating subtle gravitational influences between otherwise isolated universes. The collision of branes in higher dimensional space might create Big Bang-like events, generating new universes with properties determined by the details of the collision. Each such collision could produce a universe with different fundamental constants, different particle physics, even different mathematical structures underlying physical law. Some brane-world models suggest that our observable universe exists on a three-dimensional brane embedded in a higher dimensional space where additional spatial dimensions extend infinitely. Other branes might exist in this infinite extra-dimensional space, each supporting its own universe with potentially different laws of physics. The concept of mathematical democracy, proposed by physicist Max Tegmark, takes these ideas to their ultimate conclusion. This radical idea suggests that every mathematically consistent structure exists as physical reality somewhere in the ultimate ensemble of all possible universes. Our physical universe would be just one mathematical structure among infinitely many others. In this Level 4 multiverse, as Tegmark calls it, there would be universes based on different mathematical foundations. Universes where space has different numbers of dimensions, where time has different properties, where the relationship between mathematics and physics follows different rules, or where mathematical structures we consider purely abstract have physical reality. There might be universes based on non-Euclidean geometries, where the familiar rules of space and distance work differently. Universes where time branches and merges rather than flowing in a single direction. Universes where consciousness and mathematics interact in ways that violate our assumptions about the nature of mind and reality. Some of these mathematical universes might contain forms of consciousness and intelligence that transcend our current understanding. Beings that exist as pure mathematical relationships, artificial intelligences that arise naturally from computational processes embedded in the structure of reality itself, or collective consciousnesses that emerge from the interaction of fundamental particles according to mathematical rules we cannot comprehend. The implications of mathematical democracy for consciousness and identity are perhaps the most profound of all. If every mathematically consistent structure exists as reality, then consciousness itself might be more fundamental than we assume. Rather than consciousness being an emergent property of complex arrangements of matter, consciousness might be a basic feature of mathematical relationships that exist independently of any physical substrate. This could mean that consciousness exists in forms and at scales we cannot currently imagine. There might be cosmic scale consciousnesses that experience reality at the level of galaxy clusters and cosmic filaments. Quantum scale consciousnesses that exist in the fleeting interactions between elementary particles. Mathematical consciousnesses that inhabit purely abstract realms of number theory and geometric relationships. The question of personal identity becomes even more complex in this context. If infinite copies of you exist across infinite universes, and if consciousness itself might be a more fundamental feature of reality than physical embodiment, then what makes your particular stream of awareness special or unique? Some theories suggest that consciousness might play a more active role in determining which branch of quantum reality we experience. The many worlds interpretation of quantum mechanics proposes that every quantum measurement creates a branching of reality, with each possible outcome occurring in a different branch. Consciousness doesn't collapse the quantum wave function, but rather follows one branch among many. Combined with an infinite multiverse, this could mean that every possible version of your life, every decision you could have made, every path you could have taken, exists as a real physical branch of reality somewhere in the infinite ensemble of universes. Your consciousness threads its way through this vast space of possibilities, experiencing one particular path, while other versions of you experience all the alternatives. This perspective doesn't necessarily provide comfort in the traditional sense, since the continuity is not of personal consciousness, but of information patterns and mathematical structures. It does suggest, however, that nothing is ever truly lost in an infinite multiverse. Every moment, every experience, every thought and feeling that has ever occurred or ever could occur exists eternally somewhere in the infinite expanse of reality. The implications extend beyond individual identity to the nature of civilization and intelligence itself. In an infinite universe, there would be civilizations that have existed for billions of years longer than humanity, having solved every problem we face and developed technologies that transcend our current understanding of what's possible. Some of these ancient civilizations might have learned to manipulate the fundamental constants of physics, creating pocket universes with customized physical laws optimized for their purposes. They might exist across multiple scales simultaneously, from quantum processes to cosmic structures, integrating their consciousness and technology with the basic fabric of space-time itself. There could be civilizations that have achieved what we might call technological transcendence, existing as pure information patterns that can inhabit any suitable computational substrate. These beings might migration between different regions of the infinite universe by transmitting their essential information patterns at the speed of light, reconstructing themselves in new locations as needed. Advanced civilizations might have found ways to influence the evolution of the universe itself, perhaps guiding the formation of galaxies, stars, and planets to create conditions favorable for the emergence of consciousness and intelligence. They might exist at scales so vast that entire galactic clusters serve as their computational substrates, processing information about the nature of reality at levels we cannot comprehend. The concept of intelligence existing at cosmic scales raises profound questions about our place in the universe and the nature of consciousness itself. Are we perhaps components in some vast intelligence we cannot perceive, like cells in a cosmic brain whose thoughts unfold over geological timescales? Is the apparent fine-tuning of physical constants actually the result of engineering by beings operating at scales beyond our comprehension? In an infinite universe containing every possibility, such scenarios are not only possible, but inevitable. There would be regions where intelligence has evolved to scales and complexities that transcend our current concepts of consciousness, thought, and purpose. The universe itself might be conscious in ways that individual minds cannot grasp, processing information about its own structure and possibilities at every level, from quantum to cosmic. The search for extraterrestrial intelligence takes on new meaning in this context. If advanced civilizations exist throughout an infinite universe, why haven't we encountered them? Perhaps they exist primarily beyond our cosmic horizon, in regions of space we can never observe. Perhaps they operate using physics or technologies so advanced that we cannot recognize their presence even when it surrounds us. Or perhaps the scales of space and time involved are so vast that meaningful contact is impossible even for civilizations millions of years more advanced than our own. If truly advanced intelligence operates at cosmic scales, processing information over millions or billions of years, then our entire civilization might appear to them as a brief quantum fluctuation, too rapid and small-scale to merit attention. The concept of cosmic intelligence also transforms our understanding of the relationship between mind and matter, between consciousness and physical reality. If intelligence can emerge naturally from the interaction of matter and energy according to physical law, and if infinite variations of this process occur throughout an infinite universe, then consciousness might be far more common and fundamental than we currently assume. Rather than consciousness being a rare accident that occurred only on Earth, and perhaps a few other planets, it might be an inevitable consequence of sufficient complexity in any universe with physical laws that allow for information processing. The infinite universe might teem with consciousness in forms we cannot imagine, from quantum-scale awareness to galactic-scale intelligence. Recent developments in quantum information theory have revealed new connections between these cosmic questions and the fundamental nature of information itself. The quantum error correction codes that protect information in quantum computers might be analogous to the mechanisms that preserve information in the universe at large. The apparent stability and consistency of physical law might emerge from error correction processes operating at cosmic scales. If the universe operates like a vast quantum computer processing information about all possible realities, then what lies beyond our observable boundary might be other regions of this cosmic computation. The unobservable universe might contain the quantum superpositions, the alternative histories, and the parallel processing streams that allow the cosmic computer to explore every possible outcome simultaneously. Each region of infinite space might be running different computational processes, exploring different mathematical structures, processing different types of information about the nature of reality itself. Our observable universe might be one thread in an infinite computational tapestry, with consciousness arising wherever the information processing becomes sufficiently complex and self-referential. The anthropic principle takes on new dimensions in this computational context. We don't just observe a universe compatible with our existence. We observe the particular branch of the cosmic computation that led to our specific form of consciousness. Other branches, existing beyond our observational reach, might have computed different types of observers, different forms of intelligence, different ways of experiencing and understanding reality. The deep structure of existence may not be matter or energy at all, but information itself. Patterns and relationships woven into the very fabric of being. Space, time, particles, and forces may be emergent phenomena, shadows cast by deeper informational rules operating beneath what we can measure. If this is true, then what lies beyond our horizon is not simply more space filled with more galaxies, but the unbounded continuation of the cosmic code, endlessly unfolding new possibilities. This perspective blurs the line between physics and philosophy. When we ask what exists outside the observable universe, we may really be asking about the limits of knowledge itself, whether there is an ultimate code, a final theory, or whether reality is an infinite recursion of deeper layers of information that can never be fully exhausted. Each new discovery expands the boundaries of what we can observe, but also deepens the mystery of what remains hidden. And yet, even as our telescopes and theories reach outward, there is a sense in which the answer may also lie within. For if the universe is a vast computation exploring every possible structure, then our consciousness is one of its outputs, a self-reflective process in which the cosmos becomes aware of itself. In contemplating what lies beyond, we are participating in the very act of universal computation, extending the frontier of awareness one thought at a time. Perhaps the truest wonder is that, in a reality where infinity rules and boundaries dissolve, there is no final beyond. There is only the ongoing exploration of possibility, galaxies beyond galaxies, dimensions beyond dimensions, ideas beyond ideas. What lies outside our observable universe may never be reached by light, but it is already being touched by mind, by imagination, by the quiet human drive to ask the questions that no horizon can silence. In the end, the question of what lies beyond our observable universe may never have a single final answer. Each generation of science has expanded the horizon of the known, only to reveal new mysteries waiting just beyond reach. From ancient stargazers who thought the heavens were fixed, to modern astronomers mapping the faint glow of the cosmic microwave background, we have always lived on the edge of the unknown. And perhaps that edge is exactly where we are meant to be. The universe does not simply offer us answers, it offers us perspective. It shows us that we are part of something vast, ancient and ongoing, yet also intimately connected to it through consciousness and curiosity. The same laws that govern the dance of galaxies also shape the thoughts in our minds. The same infinity that stretches beyond our sight also lives within our questions, our creativity, and our search for meaning. Maybe the true significance of asking what lies beyond is not about crossing a boundary of space, but about realizing there may be no boundaries at all, only endless horizons of discovery. Each time we look further, we find more. Each time we ask deeper, we uncover new layers of reality, and with them, new ways of understanding ourselves. So as we stand beneath the night sky, surrounded by stars that are themselves only a fragment of the whole, we can feel both small and infinite at once. Small in scale, yet infinite in possibility. Because in the grand computation of the cosmos, in the unending symphony of reality, our act of wondering is itself part of the music. And that may be the greatest truth of all, that the universe is not only something we live inside of, but something that lives inside of us. Its horizons are mirrored in our imagination, its infinity reflected in our capacity to dream. What lies beyond our observable universe may forever remain unseen, but as long as we keep looking up, it will never remain unfelt. When we reach the outermost edges of the observable universe, we are not simply confronting distance, we are confronting the limits of knowledge itself. Beyond that boundary lies a silence that no telescope can penetrate, no signal can return from, and no light can cross within the lifetime of the cosmos. And yet, this silence may not be emptiness. It may be the greatest ocean of all, a sea of realities that stretches without shore. Cosmology teaches us that the universe is still expanding and that expansion accelerates. Galaxies at the farthest edges are not merely receding, they are slipping beyond a horizon from which their light will never reach us. Entire realms of existence are vanishing from our cosmic view, not because they are ceasing to exist, but because the expansion of space itself is carrying them away faster than light can bridge the gap. This means that every passing moment, parts of reality are disappearing over a horizon we can never cross. Our observable universe is shrinking in its own way, a finite window onto an infinite landscape. But here is where the paradox emerges. For while our observational reach contracts, the universe itself may be infinite. Infinity is not something we can picture easily, yet it carries profound implications. If space truly has no boundary, then every arrangement of matter that can exist will exist, somewhere, at some unimaginable distance. There would be galaxies identical to ours, stars identical to the sun, and perhaps even another version of you, sitting right now, watching another documentary asking the same questions. The sheer scale of infinity makes repetition inevitable. The multiverse theories go even further. They suggest that not only space, but entire universes may branch off with different laws of physics, different constants, and different possibilities of existence. If true, then beyond our horizon lies not just more of the same, but realms entirely alien to our imagination. Realities where light behaves differently, where time flows in directions we cannot conceive, where intelligence emerges in forms we would not recognize as life. These are not fantasies, but legitimate consequences of the mathematics that underpins quantum mechanics and cosmology. And yet, for all this vastness, there is a deeply human dimension. We cannot travel to these distant regions, nor can we directly confirm their existence. But we can think about them, we can imagine them, and in doing so, we extend the frontier of the universe into our own minds. Consciousness, fragile as it is, becomes the bridge between the finite and the infinite. The simple act of wondering what lies beyond is itself a participation in that greater reality. It means that the cosmos is not just expanding outward, it is also expanding inward into the depths of human thought. This brings us to a humbling realization. The universe does not need us. Galaxies formed, stars burned, and black holes devoured long before we were here, and they will continue long after we are gone. And yet, in another sense, the universe has been waiting for us, or for something like us to witness it. Without observers, the cosmos would be silent of meaning. With us, it gains a mirror, a voice, a way to know itself. The story of the observable universe is inseparable from the story of the beings who strive to observe it. Perhaps this is why so many scientific discoveries eventually circle back to philosophy. What lies beyond is not just a physical question, but an existential one. It forces us to consider our place, our scale, our role. It challenges us to face infinity without flinching, and to draw meaning from the fact that we are here at all, aware enough to ask the question. So as we close this journey, let us return to the night sky. Every star we see is both a reminder of distance and a reminder of connection. Each point of light is a messenger from the past, carrying information across time, whispering to us about the structure of reality itself. And for every star we can see, there are countless more we cannot, their light lost beyond the horizon, their existence hidden beyond reach. Yet they are there, and knowing they are there transforms the way we experience the stars we can see. What lies beyond the observable universe may forever remain unseen, but it does not remain irrelevant. It shapes our theories, it stretches our imagination, it humbles our ambitions, and it elevates our sense of wonder. In that sense, the boundary of the universe is not a wall but an invitation, an open doorway to curiosity, to humility, and to awe. And perhaps that is the greatest gift of all, that in asking what lies beyond, we find what lies within, the spark of wonder, the courage to imagine, and the realization that even in the face of infinity, we are part of the story.